This episode of the Drone Radio Show is presented by Ascent Aerosystems, the leader in coaxial drones for mission-critical operations. Learn more at ascentaerosystems.com.
For whatever reason, GPS were to completely go away, most autonomous aircraft would drift significantly to the point that they would probably have a catastrophic failure. So what we are trying to do is try to build robust technology such that the aircraft are immune to this kind of degradation or complete loss of GPS.
You're listening to the Drone Radio Show podcast, the show about drones and the people who use them for business, fun, and research. Hosted by Randy Goers.
Hello, everyone. This is Randy Goers, and welcome to the Drone Radio Show podcast, episode 300. What happens when the GPS goes out? If you ask today's guest, he would say, nothing to worry about. Sanjiv Singh is CEO of Near Earth Autonomy, a Pittsburgh-based company that is creating a future where autonomous flight is commonplace and safe. Near Earth's technology allows aircraft to autonomously take off, fly, and land safely, with or without GPS. Their solutions enable aerial mobility and inspection applications for partners in the commercial and defense sectors. Sanjiv leads the technical and business strategy for the company. He brings 25 years of experience in autonomous ground and air vehicles operating in extreme environments. His expertise is in perception and planning for air and ground vehicles. In addition, he specializes in the coordination of human and robotic teams. Sanjiv obtained his PhD in robotics at Carnegie Mellon University in 1995 and has since been on the faculty at the Robotics Institute. He is the editor-in-chief of the Journal of Field Robotics. In this edition of the Drone Radio Show, Sanjiv talks about Near Earth Autonomy, the company's groundbreaking technology, and the future of robotic flight. But before we hear from Sanjiv, I want to thank those of you who are supporting my funding campaign. Whether it's $1, $100, or much more, you can help defray the cost of production and keep the podcast going and growing. Go to droneradioshow.com/donate. And by the way, if you have an idea for a great show and want to share your experience, please contact me at randy@droneradioshow.com. So let's learn how drones can fly without GPS with Sanjiv Singh of Near Earth Autonomy. Let's pick up the interview where I asked Sanjiv to introduce himself.
Yes, hi, my name is Sanjiv Singh. I'm the CEO of Near Earth Autonomy.
Sanjiv, tell us about Near Earth Autonomy. What does the company do?
So Near Earth develops technology that enables aircraft to fly both efficiently and safely. So safety and efficiency are two things that the aviation industry cares about a lot, and especially when we're thinking about these aircraft flying without pilots, this is especially relevant here. And so we build a technology that enables the next generation aircraft to be able to fly both safely and efficiently.
Is it software, hardware, or both?
So we have a range of offerings. Some of them are software components that run on desktops even before you get flying. And then most of it is about software and hardware combinations that are on board the aircraft that provide the intelligence for these aircraft to be able to operate on their own.
So what makes Near Earth Autonomy stand out among other companies that are attempting to do the same thing?
Actually, in the exact space we're in, there are relatively few players. And how we distinguish ourselves in the aviation space is that we have technology that enables aircraft to be aware of its environment and then to act in accordance to its understanding of the environment. Okay. Now, some of this information, this environmental perception, is available through maps that could be used, either before flight or during flight. But most of it has to do with sensory data that is gathered during flight such that aircraft can actually act on the data that they find. So there are lots of applications of this, which people care about a lot. So if you take a pilot outside, take a pilot out of an aircraft, then you would still want that aircraft to act as if there was a pilot in there. So you have to replicate some of those capabilities. Say, for example, being able to steer clear of things that might not be on the map, a tower or wires or trees, buildings. A pilot might see that something is in its way on a route that it has never been to before. A pilot has not flown on before, and then be able to make a course correction. Our technology would be able to do that. If the air traffic control tells a pilot to land in a particular place and that's not a safe place to land for whatever reason, the pilot would recognize that and not land at that moment and maybe take some time to communicate with the air traffic control. So we want these aircraft to be able to do things like that. And our technology enables such capability.
What markets are you primarily serving?
Yeah, there's recently a nice way of putting it that what we're interested in is packages, patients, and passengers, 3 Ps. And the idea is that cargo is a low-hanging fruit that a lot of people care about, moving things from point to point, which is relatively low risk because you're carrying cargo and not people. Then there is an issue of carrying patients, some sort of emergency application, possibly getting wounded people or people hurt in some sort of case very quickly to medical help. It's sort of in the middle. And the last use case that we look at is a case of carrying passengers. So just like a self-driving car, only an aerial version of that.
Can you tell us about some of the system's capabilities?
Our core offering has to do with 7 or 8 very specific kinds of use cases or capabilities that have to do with mission planning, that have to do with obstacle avoidance, which is avoiding things that are static, collision avoidance, which is avoiding other aircraft by sensing them, not just being dependent on any signals that are emitted from these aircraft. Then being able to deal with a kind of component failure, we call that contingency management. Something fails on the aircraft and vehicle needs to come down very quickly. How to do that. Being able to do with a loss of GPS. These days, most of the aircraft that are operational today, if there was a loss of GPS, either it was degraded or jammed for whatever reason, autonomous aircraft would have a difficult time flying stably. So we have to be able to allow these aircraft to fly through an interruption of GPS. We have a couple of other things that have to do with safe landing and then precise landing. Safe landing is wherever you're landing, whenever you're landing, make sure that that place is actually clear to land. And precise landing is some sort of system that helps aircraft land very precisely. Now, you can get some safety through precision. That means that the landing area is nominally marked as safe. So through some communication between the ground and the air, very lightweight infrastructure, you can set up a way that enables aircraft to land very precisely. So those are the common cases that we're looking at.
The company's website characterizes Near Earth Autonomy as bridging the gap between aerospace and robotics. What does that mean?
Yeah, so when you look at traditional aerospace, that field, which has now become pretty mature, has to do with the design of the aircraft. It has to do with propulsion, with what we call inner loop flight control, which is to make sure that the aircraft can fly stably and it can go in a particular direction. So that set of capabilities is a very well understood discipline now. Of course, we're always coming up with some innovative aircraft and different ways of doing propulsion to different kinds of design that enable efficiency, et cetera. But the outer loop, which is how we actually guide these aircraft autonomously such that they can go from A to B, stay away from any hazards, detect hazards, and then avoid them in real time. That is a set of technologies that is very familiar to the robotics world and is not so much there in the traditional aerospace world. So what we are doing is, as a group of people who've been very familiar with robotics, mostly ground robotics or ground vehicles that drive by themselves, we've taken some of those ideas and sort of brought them into the aviation world. So we bridge that gap. It's not easy to go from simple or sort of mainstream robotics into aviation because flying aircraft is actually a fairly complex business, and the liability involved in the sort of regulatory framework is fairly complex. So you need to have kind of a foot in both doors to be able to do this. Just because you're a robotics expert doesn't easily set you up to do autonomous aircraft. So we bridge that gap.
Air mobility is one of the industries that Near Earth Autonomy serves. How do you support that sector?
So I gave you this description of these value propositions, right? Starting from mission planning all the way to landing precisely and landing safely. What we do is we have software and hardware components that we make available in a configurable basis to early adopters. So what we do is we talk to companies that build these aircraft, and often they have some, at least to start off with, they have a pretty firm ideas on what they would like to augment the actual vehicle themselves. Sometimes they have just a bare bones of the inner loop, and they're looking for as much as they can get to provide this safety from takeoff to landing. In some cases, they actually have quite a lot of it done, and they have a sense that they're looking for one or two or three of these capabilities, and others don't matter in their use cases or don't matter to start off with. And so what we do is we bring these hardware and software components, configure them, and are able to get them going into flight testing in some cases just weeks. That's the kind of value proposition that we've established, is work with early adopters to be able to figure out what kind of problems are worth solving, such that then we can go on to doing a deeper integration between the aircraft and the kind of autonomy components we provide.
Is it the same with inspections, or is that a different type of service?
On the inspection side, that's a very different world because it's less of a horizontal, less of an industry horizontal where we work with all kinds of companies to do it. Because in the inspection space, what's monetizable or where the money is in the data that the aircraft get. So we're looking at specific verticals in which we would have complete solutions that start with the aircraft and then end with data that can be analyzed to make decisions. And so it's almost a completely different value proposition as opposed to in the mobility sector, which is horizontal. The core technologies are the same. And of course, a lot of the experience in actually formulating the problems and then actually executing on these problems are the same, but the value proposition is almost entirely different, completely different between the mobility and the inspection sector.
Can you talk about the opportunities in the inspection sector?
The inspection sector side of the business is actually very, very wide open, and we're trying to focus in the area in which we think there is a good intersection between our core technology and there's a good market case. There are literally hundreds of applications of inspection. So you might be inspecting a wind turbine or a furnace, a large furnace where you're flying inside the furnace to make sure that the structure is sound, or fuel tanks or water tanks, et cetera. So what we're looking at here is a few use cases in which we can take our key technology and be able to connect it to a case where there's a sustainable business. So I'll give you an idea of where there's a match from a conceptual standpoint. What we're looking at is that the value is in taking repeated measurements, rapid repeated measurements over time that can be very accurately tagged to some common reference frame. Okay, and this seems to be a very common kind of a need there. So for example, if I have a bridge or a water tank or fuel tank, let's just take two kinds of things, right? These are things that are worth inspecting. What you want to do is you want to go and be able to take some pictures, or maybe there are some other kind of data, maybe they're thermal, maybe there's some other kind of sensor that would give you a measurement of thickness of a coating. And you want to be able to register that measurement very precisely to a location. Okay, so let's take a fuel tank. If I go and inspect that fuel tank for the thickness of the coating, I want to know exactly where I took those kinds of measurements so I can build some sort of an analysis on whether the tank is sound from the perspective of holding its contents. And then maybe after some time, I want to go and do that again, such that we want to be able to track the structural fidelity of some structure over time and make sure that there aren't any kinds of changes in that thing. So if you get any kind of a measurement, as long as it's stable, it might be okay. But if it's changing, then you know that there may be a problem over time. So this is a very common kind of a use case, and it's a very specific kind of take that we have on inspection, and we're looking for a few really good examples where there's a need and it could build a sustainable business around it.
Does the system automatically catalog or recognize when there's a change in whatever it's inspecting, either structural integrity or defects?
That's a really great question. There really actually like 3 steps to some inspection I could think of at a very high level. First is you want to fly precisely and safely, on some sort of path that's been designated and that you could get the data. Okay, so that's number 1. Number 2 is you want to take that data and you want to register it very, very accurately to some common reference frame. And number 3, you take that data, you analyze it such that you look for defects. Okay, and these are actually 3 very different kinds of things, and that's why we need to build this vertical, because without all 3 of them, you don't really actually have a viable use case. In fact, in a successful vertical, you'd be doing all 3 of those.
What's the company's philosophy on sensors? And how does the system integrate multiple sensors?
When we put sensors and computing onto an autonomous aircraft, we have to take a lot of care to how we put these things together, because in the first part, autonomous aircraft or any aircraft, small aircraft that you'd use for inspection is going to be sensitive to the weight that you add onto the aircraft. Small aircraft have limited endurance, and every gram that you put on the aircraft is a direct hit on the endurance of that aircraft. So we have to absolutely optimize the amount of the weight and how the structure that holds these things together. Another thing that we work hard on is try to make sure that we can temporarily register the sensor data such that you can correlate different sensors over time. So if you're getting data from an IMU and you're getting data from a camera, you're getting data from LiDAR, they're all coming in at various different rates, and they're all taken from various different locations as the aircraft is flying, and you have to merge them together. So what you have to do is you have to find a way to at least be able to recover that temporal registration such that you can merge this data. Even if it's hovering, it's not really still. So you have to be able to cancel the vibrations and still at the same time be able to get the nuances, minor tilts and rolls of the aircraft such that you can register all this data together. So it takes some expertise to put all this together and put it together in a small form factor such that you can actually fly it on the kinds of aircraft we use for inspection. So that's one of the cases that we use. Even on the larger aircraft, some of these issues are still there. We have to point the sensors in some cases, or we have to be able to determine the attitude of the sensors very, very accurately because they may be moving as the aircraft is moving. And so, again, there's this issue of being able to have something that's mounted to the aircraft, is able to reject the vibrations from large rotors, for example, but still be able to register the data that's coming at all kinds of different 2 or 3 orders of magnitude difference in the frequency of the data and put it together. In many cases, we need to make that decision, need to register it, and then be able to understand it or to parse it in real time. In some cases, we can just log the data and process it later. In any of these cases, it takes some expertise to put these sensing and computing modules together and then to be able to mount them on aircraft.
One of the things that Near Earth Autonomy does well is helping drones operate when there is no GPS signal. Can you expand upon that?
Most aircraft are dependent on GPS to tell them where the aircraft is. And now, depending on the sophistication of the aircraft, if some reason GPS were to be denied or a GPS receiver were to fail, or a more common case might be that some part of the sky, the constellation, is shielded. So if an aircraft flies next to a building or terrain, you may not be able to see some of the satellites. So, GPS is degraded. So the issue is then, how does an aircraft depend on this? In the worst case, if for whatever reason GPS were to completely go away, most autonomous aircraft would drift significantly to the point that they would probably have a catastrophic failure, or their navigation would drift to the point that they would have a catastrophic failure. So what we are trying to do is try to build robust technology such that the aircraft are immune to this kind of, degradation or complete loss of GPS. There's also a case that, we have to protect against. Everybody who's thinking about flying autonomous aircraft regularly in the national airspace has to worry about this, which is, yes, of course, there's degradation of GPS when you get close to structures. And so if you're coming into land in an urban environment, you might have some shadowing and you lose some precision there. But there's another case, which is you have to be able to deal with malicious jamming of GPS. And it doesn't take much. You could have technology in the form factor of a soda can that costs a few $100s that would jam GPS in a few 100 meters. Okay, so for whatever reason, just like we have people who hack systems or try to break into all kinds of computing infrastructure, I think we have to be able to prevent that kind of hacking or that kind of loss, that kind of jamming. And so we'd like to be able to have aircraft that are immune to that. So all the way from takeoff to landing, they should be able to fly and not be affected by degradation or loss of GPS.
Is that difficult to achieve?
For a roboticist, this is not a very big deal. Somebody who works in robotics, we call this state estimation, and you need to be able to solve this problem. In many cases, GPS is just absolutely not available. If you're working inside a building, then you have to be able to solve these kinds of problems anyway without actually requiring infrastructure to be installed in the scene there. So what we do is we use sensors to do at least some version of what we call dead reckoning. So you can use sensors. So if you use cameras, you can do something called visual dead reckoning, which is essentially you track salient features in visual imagery and be able to figure out how the vehicle is moving over time. Okay, whether it's a ground vehicle or air vehicle, we use the same kind of technique. Now, this is like any kind of dead reckoning, whether you're doing with an IMU only or you're using an inertial instrument plus a camera. What this is some version of counting your steps. Just like a blind person is doing this, counting their steps, we would do that. This is a simple method, and our methods, even though they're simple, they've got much better, and we can get about 2 to 3% of distance traveled in the case when you have visually clear conditions. You don't have to have any kind of a map or anything else like this. The camera produces imagery. We automatically detect salient features. We track these salient features. And over time, we can get navigation that's good to about 2 to 3% of distance traveled. Now, what this means is that if you fly for long distance, you'll be far away from where you think you are because you're guaranteed to have some sort of a drift, and 2 to 3% will add up over time. So there's a next level of correction that we do is to recognize some sort of a feature from a previous map, either in a digital elevation map or a satellite map, and make a correction such that the aircraft recovers any kind of drift that might occur. Okay, so you could take what we call a DEM, a digital elevation map, commercial map that's available. That means pretty much everywhere in the world, for every 10 meters, you have one elevation. That would be a simple way. If you could sense the terrain using some ranging device, you could actually match what your sensor is seeing versus that elevation map and use that as a correction. Okay, so that's a second level of correction that you can use that can basically cancel drift. Now, that's not always possible because your aircraft is flying pretty high and you can't actually range to the ground. Or it could be because, any other kind of condition like that you might not have such a device on the aircraft. So we also look at satellite maps, and, just like you would look in a Google map, there are some features. You look at the map and you look at the image from that the aircraft is collecting, and you correlate the two and use that to cancel your drift.
I read recently that Near Earth Autonomy is involved with NASA on a project involving urban air mobility. Can you tell us about it?
The idea is that NASA is very interested in basic technology that will allow aircraft of various sizes, scale, morphology to be able to fly in national airspace. Of course, they have big interest in the the fact that these aircraft can stay safe so they don't collide into things, and of course that they can navigate successfully in the kind of case that I talked to you about of degradation of GPS. So we are working on a couple of themes in urban air mobility, which is autonomous aircraft that can use satellite maps, or they can use some prior imagery to be able to navigate in case GPS is lost. So that's one kind of thing we're working on. The second thread that we're working on is safe landing. And the idea is that we have already some technology in that area, but in the national airspace, what could happen is that there could be moving objects at the place where you're landing, and they could be vehicles, there could be people. And so you want to be able to recognize that there are objects in the scene where you're coming into land that are moving, and be able to still be able to land safely. And so those are two of the main things we're looking at. There's a third theme, which has to do with how would we deal with some sort of a contingency that occurs where something fails in the aircraft, and how can we actually pre-plan our path such that there's always an option to land safely if at any second something were to go wrong. So we don't want to start looking at that time for safe places. We already have a list of places that are safe to land, and then we choose between those places and actually land safely.
One thing that I noticed from the website is that it appears that the company is involved in a wide variety of projects. Is there a common theme?
There are quite a few commonalities. I think at the highest level of commonality, there's this issue of whether we're thinking about mobility or we're thinking about inspection. This is the highest level bifurcation, right? In inspection, what you're doing, whatever the aircraft and whatever you're sensing, is that the aircraft is the very start of a long workflow in data analytics that gathers data. When the aircraft lands, that's just the start of the data analytics. So that's a kind of its own world here in terms of technology and, what kinds of things we need to enable, the kind of registration we have to do. On the mobility side, you take off and you land, and when you land, the job is done, right? So the job is about transport of something. And you could think about the inspection as a sort of transport of a sensor, but I think it's best to think about these mobility applications in a completely different way, because it has to do a lot with the kinds of flight profiles you have to fly. In some cases, the requirements of the flight profiles create very different solutions. Okay, so if you have a military use case where you have to worry about threats, and you have to fly very low, and you have to come in at a very shallow glide slope, might have to land into an unmapped landing zone without any hover or overflight. Now that's going to result in a very different kind of a solution. And we've been trying to find, okay, there's these kinds of art of the possible kinds of projects where we're looking for what's hard, but over time, what we're thinking about is like, what is the art of the practical? Like, how can we actually bring together some of these requirements into infrastructure or some sort of common set of technologies from which we can exploit an economy of scale? In fact, that's what a lot of our work today is, that even though the aircraft might look very different, it might have wings or it might have rotors, but when we look at many of the transport applications and we look at their flight profiles, or look at the speeds at which they fly, we can typically bring it down to some combination of the technological elements that we have.
Turning to yourself and your involvement in the company, would you describe yourself as coming from the robotics industry or from the aerospace industry?
No, I come directly from the robotics world. I got a PhD in robotics at Carnegie Mellon, and then I've been on the faculty since 1995 at Carnegie Mellon. These days, I'm more in an adjunct role at Carnegie Mellon. But I sort of mainstream robotics. My background was in robotics for unstructured and what we call field environments. There's a subset of robotics we called field robotics, and that was my specialty. So I was working in that area for all sorts of applications, mostly ground vehicles, for half my career. And then starting in the early 2000s, I got very interested in air vehicles and had to learn a lot about aerospace. That was certainly not my background.
Where did the idea to start a company come from?
Yeah, actually, that's an interesting story. We could talk for a long time about it. But essentially what happened was we had a large opportunity for which we couldn't make it work at the university. It was large enough that the terms that that opportunity came with were not acceptable to the university or not easily acceptable to the university. So what we did was we wrote a proposal and said, okay, if this project comes through, then we'll start the company. And that's exactly how Near Earth got started. There's been a couple of other companies that have started, but this one started that way. We said, all right, let's try. It's big enough a thing. We'll write the proposal and see what happens. And in fact, then the proposal got funded or got selected. And we said, okay, now we have to start the company. It's sort of not a common way to start a company. And I wouldn't even really advise it to others. But okay, that's how Near Earth got started.
Is this your first company?
No, this was the third one. And there's been another one since then that we forked off from Near Earth. But, the idea was that I had always been on the applied side and been sort of interested at it, but had enough sort of experience to know that it's easy to start one, but it's really actually hard to keep it going. So there was this idea that you need some critical mass to get going. So we were pretty clear about that at the front end, was that to get a successful company going, you need to have some monetization. So you don't just start the first thing and then start looking for money right away. So the opportunity that presented itself was a 5-year opportunity. There was some gates in the middle. And, it was sort of like a project of a lifetime. So I thought, okay, this is worth actually going out on the limb for. And got lucky in a couple of ways that right after we started the company, the aerial robotics world or drone world actually got very hot. And that was, I'd say, more happenstance than anything else because, it's hard to control timing. Some components became available in terms of sensors and small aircraft that just weren't there before. So there were many, many, many opportunities presented. And so we started with 4 people, and now, a few years later, we're 85 people. And what led to that was there was just a very large explosion of use cases that presented themselves. And then very quickly, we got involved in a bunch of them.
Looking back at the original idea for the services that you were going to provide, how has that evolved to what you're delivering today?
So I have to say that we had a very basic kind of idea at the front end and not this sort of very specific service or product that we were thinking about. So for most of my career, I've been working on self-driving cars. And, in the very early going, there were no real clear applications. So that was okay, for us, for people who'd been doing research in this. It was just good enough that there were applications that for cars or tractors or trucks to be able to drive by themselves. We could see some applications. We didn't know how they would get into play, so we went into it at the very early going. I started working in this in 1985 for 15, 20 years easily. We were working hard on the technology, solving problems we knew without thinking about the application. So when the opportunity presented itself, it was a similar kind of thing. It was a big opportunity to take a full-scale helicopter and have it fly autonomously, kind of the way we've been working with ground vehicles, fly from A to B, stay safe, okay, and do it under very challenging conditions. So this was, a challenge of our lifetimes, very well monetized project. So we just jumped into that and felt that, okay, we'll see where it goes. We'll take it when the applications become evident. And then, over time, real applications became evident, and it became very important for us to think about specific use cases, how to tailor our technology to match real problems that people have to solve. And so over time, we've sort of started to focus on actual products.
What would you say the last few years have taught you?
That's a great question. I try to think about this all the time, practically on a daily basis. So if I had to say one thing, I would say that good technology does not equal good products, okay? And good products solve real problems. And so I tell myself this every single day because, being technologists, it's easy to convince yourself that good technology that has, even interest from a lot of people will automatically turn into good products. But good products actually need to be sustainable, and they need to solve people's problems at a certain price point, and they need to be reliable and easy to use. And I think that thinking about demonstrating technology is one really important step, but building good products is just a completely different game altogether. And I would say that that's the challenge we've been as a company struggling with for the last couple of years. I think we're making some headway, and there's some really exciting things that are in the pipeline, but that is the lesson that I have to remind myself and talk to our team about.
What's next for Near Earth Autonomy?
So I'd say there are two threads we're somehow or the other maintaining. One is some real visionary technology that makes things possible that haven't been possible before, some use cases that you haven't seen. We're working with some really neat helicopter technology or helicopters and automating those and sort of going back to the way of operating that we've done before, which is there is a nominal use case. We're not thinking about the product as much per se. We're trying to demonstrate that something that's never been done before is possible. So that's one stream, and it's a very exciting kind of a thread. And basically, we're sort of always evolving the technology, making it more efficient, more reliable, and easier to use, that kind of thing. But it's the concept of just like the people who are working on the self-driving car world, they're showing improved technology over time and trying to make the case for turning these into real services. There's another link which has to do with building market verticals for the inspection side, and we have a couple of hot areas that we're working on that we aren't public about yet, but I think we will be in the near future.
I'm curious, is there a story behind the name of the company, Near Earth Autonomy?
Yeah, so, we wanted to think about autonomy for aircraft, but if you think about aircraft that are flying by themselves, there are many cases where they're flying at high altitude in which the kinds of considerations that you have are completely different. So if you have aircraft that take off from runways and then fly at high altitude, surveillance aircraft that you probably are aware of, that's a completely different set of technologies that are necessary. When you're flying at low altitude, and low altitude didn't quite have the same ring as near Earth, right? So low altitude autonomy doesn't sound like a name of a company. But when you're flying at low altitude, you have to be really aware of the environment. A lot like, the kinds of things we were worried about from the world we came from, which was the ground vehicle world. And so after much discussion about how we were going to name this, I think the idea was that Near Earth also means different things to different communities in the space world. It means hundreds of kilometers from the Earth's surface, but we settled on Near Earth as a kind of a way to sort of capture the essence of what we do.
Is there anything that we missed that we should talk about?
As a company culture, we think about impact and growth, right, as a way to grow. Growth is like personal growth, how we grow individually and what we learn from the work we do. And then another thing is like, how are we actually changing the world? So we spend quite a lot of time thinking about that and sort of like in connecting to the use cases that are out there. Some use cases are nascent and they really aren't established, but if we could connect our technology to these use cases, then it would make a difference in the kinds of challenges that we have today. So we work hard on trying to match those, and rather than just being a technology company that's driven by curiosity. Of course, that is the key idea that brings innovative solutions, but we have to be able to connect it to these kinds of problems. Otherwise, there's a question of what are you doing this for? And I think that's a question I've been spending a lot of time thinking about. What is this technology good for?
And for my final question, Sanjiv, what message would you like to leave regarding how Near Earth Autonomy is going to revolutionize the drone industry?
So what we said as a goal is that we are establishing an industry standard in aerial autonomy to make autonomous aircraft commonplace, right? So I'm not sure I'm saying that in a succinct enough way or lyrical enough a way, inspiring enough way. But I think the idea here is that we want to build an ecosystem of technologies. It's not just one or two technologies that enables aircraft to fly safely and efficiently. That is from a technology side, and then what we'd like to connect is real problems that need to be solved in the near term.
That's it for episode 300 of the Drone Radio Show. I hope you enjoyed hearing from Sanjiv Singh of Near Earth Autonomy. I want to thank Sanjiv for taking the time to speak with me. If you want to learn more about Near Earth Autonomy or want to connect with Sanjiv, check out the webpage at nearearth.aero. That's nearearth.aero, aero. If you like the Drone Radio Show, please consider supporting the podcast with a small donation. The content is always free, but for as little as $1, you can help defray the cost of production. To donate, go to droneradioshow.com/donate. And thanks for listening. Your support means a lot to me, and I hope you'll listen to more episodes of the Drone Radio Show podcast to hear how others are using drones for business, fun, and research. For the Drone Radio Show, I'm Randy Goers.
This has been the Drone Radio Show podcast. More information on today's show can be found on our website at www.droneradioshow.com. If you're using drone technology for business, fun, or research and would like to share your experience on the show, please visit our website and fill out a guest appearance application. And don't forget to follow us on your favorite social media channels.